Welcome to Climate Chat. I'm your host, Dan Miller, and today we're going to do something a little bit different. I gave a lecture earlier this week at the Middlebury Institute of International Studies at Monterey, California, and it was a summary of the latest climate science. It's something that we actually talk about a lot here on Climate Chat, and the information comes from the interviews we've done with people like Jim Hansen, Leon Simons, George Tselioudis, and others. But I thought this would be a nice way to sort of, even if you've been following the show and sort of aware of that, it might be a nice summary and to put it all together in context. And also for those of you who are new, it's a great way to learn about the latest stuff without having to listen to all the past shows. So without further ado, let's get into the talk. And let's see, it's called Climate Science Update and Conservation Policy Considerations. Today, we're only going to be talking about the climate science update portion of the talk. And on a later show, we'll go into the policy implications and things to avoid when designing climate and conservation policies. But as I mentioned, today we're going to be talking about climate science. So let's switch to a full view here. So these charts here show sulfur emissions around the world. On the left is a global map showing sulfur emission, and the red is sort of the highest, and the yellow is also high, and blue, light blue and blue are less. So you'll see the reds are mostly over land, and that's where there are coal plants and steel mills and that kind of thing emitting sulfur from the burning of fossil fuels. But you'll also notice that in the North Atlantic and North Pacific regions, there's also a lot of sulfur emissions over the ocean. And that, of course, comes from shipping. And this is from 2010. So this is before a policy implemented by the International Maritime Organization, or IMO, was implemented to lower the sulfur content of shipping fuel. In fact, it was about 80% reduction in 2020. So what happened then is ships were still obviously sailing everywhere, but the sulfur emissions they gave off were much, much less than they were even the year before. It did lower, I think it was starting in 2015, but by 2020, the full impact was in effect and a dramatic reduction of shipping. So this was done. Why did they do this? Well, burning fossil fuels is dangerous, actually, and for human health. In fact, a Harvard Medical School study showed that 8 million people a year die from particulate matter from the burning of fossil fuels. That would be sulfur and PM 2.5 and other things that you breathe in, and that causes cancer and heart attacks and all these other things, breathing issues. And so it's a very big problem. And so the IMO knew that sulfur is bad for human health, so they decided to implement a policy that would change, to lower the sulfur and therefore make it safer for human health. Even though, by the way, it's obviously over the ocean where not too many people are. The red areas are the areas where most of the damage is done. But if you look on the right, the blue line shows the drop in from 2019 to 2020 of a very dramatic lowering of sulfur dioxide emissions. And on the sort of orange line, you see that going up. That's absorbed solar radiation. That's how much energy the Earth is absorbing from the sun. And what happens is that the sulfur particles themselves can reflect the sun and therefore keep the Earth a little cooler. But even more importantly, those sulfur particles help create, form like the nuclei of clouds, and they help form clouds. They make clouds last longer, and they make clouds brighter. And those effects obviously reflect a lot of sunlight. And so it's the combination of those two things, the sulfur itself reflecting the sun and then the creation and the lengthening of clouds and brightness of clouds that help keep the Earth cool. So this you could consider to be solar radiation management or solar geoengineering, but the reason it doesn't qualify is because we're not doing it for the purpose of lowering the temperature. We're doing it for we were emitting sulfur because we just wanted chips to go around the world and deliver goods. So a sort of accidental solar radiation management or accidental solar geoengineering. So that's a little bit of and so this change, this policy, not only changed the climate by making the Earth warm rapidly, as we're about to see, but it also changed climate science because this was an experiment where we had a certain amount of sulfur one year and we had much less the next year. And therefore, you could take a look at that and learn things about how sensitive the climate is to greenhouse gases and to aerosols. And I should say that these sulfur emissions or sulfur pollution is also called aerosols. And so we're going to use the word aerosols mostly in this presentation. So, and one of the people that did a lot of research on this is actually our co-host, Leon Simons, who you've seen on the show previously. He contacted Jim Hansen and talked about this, and they decided to do a paper called Global Warming in the Pipeline, which also has many other co-authors on it, by the way. And just for you, those of you who don't know, James Hansen is one of the best known climate scientists. He testified to Congress in 1988 and warned that we're about to see the global warming signal come out of the weather noise. And he made a whole bunch of predictions like the opening of the Northwest Passage, wet areas getting wetter, dry areas getting drier, and on. And all of those came true. He also wrote a paper in 1982 that was published in Science, where he made predictions about the temperature and all of these things. And that, if you look back on that paper, you'll see it was very, very accurate. Anyway, Jim worked with Leon and others and did this paper, Global Warming in the Pipeline. He also did another paper more recently, Global Warming Has Accelerated. Are the United Nations and the Public Well Informed? And again, if any of you want to really dig deeper, we have covered both of these papers before. We've interviewed Jim Hansen. We're going to do another interview with him coming up, hopefully pretty soon. And so there's lots and lots of information. But today we're doing sort of a high-level view of this research. So very importantly, let's take a look at the temperature graph. And this is the global surface temperature. So global means land and ocean. And surface temperature means 2 meters above the surface, kind of where we live. You have to watch out. Sometimes people try to show you upper troposphere temperatures taken from satellites or other kinds of things like that. Or by the way, if it's the ground temperature, that could be much, much hotter than 2 meters above the surface. So this is the one when we're talking about global warming as 1.5 degrees C targets, 2 degrees C targets. We're talking about the surface, global surface temperature, 2 meters above the Earth. And C is for Celsius versus Fahrenheit. And everything we're going to talk about today is in Celsius. So we see that from 1880s, it's around when the Industrial Revolution was really gearing up. You'll notice the temperature didn't really go up a lot. And the basic reason for that is that we were emitting aerosols or pollution very fast, and it was gearing up pretty fast then. And of course, we were emitting carbon dioxide or CO2 into the atmosphere. But the CO2 effect of warming is a cumulative impact. In other words, it doesn't matter how much CO2 we put out every year. It only matters what is the total amount we put out. And back in those early days, the total amount was still pretty small compared to today. In fact, as we'll see later, we so far emitted 2.6 trillion tons of CO2 into the atmosphere. And we'll cover that a little bit later. But in these early years, basically the smoke from the pollution from burning fossil fuels was offsetting the cooling and sometimes making the Earth even cool faster than it was warming. And then you'll see little blips around World War II. And then after World War II, we industrialized rapidly around the world, especially the United States. And that kept global warming from rising because we were basically putting out lots of pollution there, even though by that time, the cumulative amount of CO2 was fairly substantial. And then in the 1970s, we passed the Clean Air Act, and other places passed similar things. And we started cleaning up this pollution, and that's when the temperature started rising very rapidly. But something happened in the last few years that's worth taking a look at more closely. So let's zoom in on the last few years. So here, the green line is what the trend was from 1970 to about 2010. And the purple line is the trend line from 2010 till the present. And you'll see they diverge quite a bit. The green line is about 0.18 degrees Celsius per decade. In other words, we're warming almost 0.2 degrees every decade. But the purple line is about twice that, 0.36 degrees Celsius per decade, or close to 0.4. And so let's take what happened. So in 2010, which is, if we go back one and we see that, let me see, let's go to full page here. So I'm sorry, I meant 2020 when we passed the rule. That's on this line. So we'll look at it more closely here. So right here is when the ship change came into effect. And you'll notice that the temperature dropped. You go, well, wait a second, the temperature should go up if we reduce aerosols and let more sunlight in. And that's true, except what was also happening then is there was a La Niña. And so La Niña and El Niño are ocean phenomenon that it's basically a warming in the Central Pacific or a cooling in the Central Pacific that signifies, since the oceans hold 90% of all global warming heat, when that middle part of the ocean in the Pacific gets cool, that actually cools the Earth a little bit. And when it gets warm with El Nino, that warms the Earth a bit. So what was happening is even though the Earth should have been warming, it dropped because of the La Nina. But let's look at this a little more closely. When there's a La Nina, the temperature should be below average. And when there's an El Nino, it should be above average. But take a look here. This line, these 2 points, these two La Nina years are on the previous trend line, not below it. So that tells you that that's not really the trend line anymore, because La Ninas should be below the trend line. And of course, they are below the purple trend line. So that kind of indicates that maybe something has changed. And then what happened in 2023 and then 2024 is we had the beginning and then the sort of continuance of a warming El Nino, and that makes the world warmer. But so now what we're seeing is that it's, again, much, much higher than the previous trend line. So this is an El Nino coupled with warming from the shipping pollution reduction, or the aerosol reduction from shipping. And again, let's just look at that again. If you see this purple trend line, the purple trend line is caused by this change in the pollution, for the other things too, maybe, but for the most part. And the La Ninas are below the trend line and the El Ninos are above the trend line. So that really is telling us something. Now, we're going to look into that a little bit more in just a bit, but I think that's really interesting what you can learn by just zooming in on the temperature graph. So this is not a model. This is not a prediction. This is just measuring the temperatures around the world and coming up with the global temperature. So this chart here, which looks like just the muddle of colors, is really, really interesting. And it tells you why the Earth is warming so much. So what this is SST, or sea surface temperature anomaly. So in other words, the change from normal, There's some base time, and then they're going the temperature changes from that base time. And what we see on this scale, on the Y scale, it's latitude of the Earth. So every particular point is the entire ocean at that latitude. So up here, this would be like around the North Pacific and North Atlantic. And down here is the South Atlantic and South Pacific, all combined into a sort of a single point. And then the bottom axis is time, going from year 2000 to 2025. So what we see is, first of all, as it gets sort of darker colors, as we go from left to right, that's global warming. That's the Earth getting warmer overall. But we also see that there's some things happening here. When you see these little red spikes near the equator, or 0 degrees, those are El Niños. And when you see sort of the lighter yellowish or the light orange, these are La Niñas. So here's a La Niña, La Niña, and La Niña, La Niña. And these are the La Niñas we were just talking about here. And then what happened is in 2023 and 4, there was an El Niño, and that's shown as this dark red, and that helped warm the Earth. But wait a second, there's something happening up above. Starting in 2020, which is this line here, we started to get a red area in the North Atlantic and North Pacific region. In fact, it got so warm that it even started moving to the light purple color here, which is the warmest of all, which doesn't even show up in the El Nino area, the Central Pacific area. And so this is what's caused by the change in shipping. Now, we did get some warming starting in 2020, but look, it was offset by the cooling of the La Nina, so they sort of canceled out. And then when the El Nino formed, this was also forming, and you sort of had a double warming, because from 2022 to 2023, it went up about 0.4 degrees Celsius, when the expectation for an El Nino would be to warm about 0.2 degrees Celsius. So there was an extra 0.2 that the mainstream climate scientists couldn't explain, and that you can explain it by looking at this warming in the North Atlantic and North Pacific. Now, there's something interesting happening when we see this little bit of the purple showing up here, where this is getting really warm in this area. And Jim Hansen, who, along with Leon Simons and others, published this information. He's now made a prediction about the 2025 temperature. And he's saying that this warming is going to offset the fact that the El Nino has faded and now is just a neutral. It's not a La Nina or an El Nino, just a neutral. And this is going to keep the 2025 temperatures to be about as warm as the 2024, even though the El Nino went away. So that's a kind of an amazing statistic. So even though this graph, you kind of haven't seen this, most people haven't seen this graph, and it looks like a jumble of colors, when you start to understand what's in it, it's really interesting, because it helps you understand what's happening. Because there are climate scientists that don't agree with what Jim Hansen has been saying. They say, well, we don't know. They don't give it their alternate explanation. They just say, well, it's maybe just random variations with the El Nino. But when you take a look at this graph, it's kind of hard to argue that it's not something to do with the North Atlantic and North Pacific, where we happen to greatly change the aerosol loading in that area. So what were some of the major findings from this work that Jim and others did? Well, one is they made a bold assertion about the equilibrium climate sensitivity. And what the ECS is the expected warming of the Earth from a theoretical doubling of CO2. So you double the CO2 concentration. How much does the Earth warm in the, quote, short run? And by short run, it's not really short, but what it means is by feedbacks that happen quickly, but not those that take a really long time. And the ones that take a really long time are things like the change, the ice on Antarctica melting away and therefore exposing dark land underneath instead of white reflective ice. Same thing for Greenland, and long-term changes in the carbon cycle and things like that. So that's what ECS is. And the IPCC said their best estimate for ECS is 3 degrees Celsius. But Jim Hansen said, look, we did this experiment with the ships. We also looked at ice age temperatures to see what happened when CO2 was much lower than before. And there's updated information. Let's use that. Let's use let's use climate models. Let's use everything and figure out what ECS is. And he came up with 4.5, which is 50% higher than the IPCC's work. And what does ECS mean? It sort of means that the warming we will experience from the greenhouse gases we have already emitted is higher than the IPCC says. But then you might say, well, wait a second, but the temperature is what the temperature is, and the IPCC knows what the temperature is today. So why isn't the temperature higher? It says, no. But Hansen is also saying that the cooling from the aerosols is also higher than what the IPCC says. So in other words, so you get higher greenhouse gas, and you get higher greenhouse gas warming, and you get higher aerosol cooling, and together they give you the same temperature as the IPCC says. But what's behind those temperatures are quite different. And over the oceans, not in general, but over the oceans, Hansen says that the cooling from aerosols is almost 10 times what some IPCC scientists said aerosol cooling is. And the reason for that is that over the oceans, there isn't any other pollution to reflect sunlight. And so even a little bit of pollution there has a big impact. Whereas if you put some more pollution over China, let's say, where there's lots of other sources of pollution, it's not dark blue water underneath, but maybe lighter colored land and things like that, that changes to aerosols there won't have the same impact as reducing even a little bit of pollution over the oceans. And again, with the cloud feedback and everything like that, that makes it even bigger. So they came to the conclusion that there's a lot of warming in the pipeline. In other words, just from the greenhouse gases we've already emitted, there's going to be a lot of warming, especially as we clean up pollution in the future. And so we're at the 1.5 degrees Celsius warming number just about now. You could argue a little bit plus or minus, but just about now, or over certainly the next year or so. Depends how you look at the trends. But I think it's safe to say that going forward, especially if Jim Hansen is right, the average temperature from now on will never drop below 1.5 anymore. And Hansen also says we're going to hit the 2 degrees of warming in the 2030s to as late as the 2040s, whereas the IPCC thinks it's closer to 2050. But again, we're going up at twice the speed we were before 2010. We're warming at twice the speed, according to Hansen. And there's something else that's interesting, and this comes into a prediction that Jim Hansen made. And that is that the higher ECS means a longer response time to climate forcing. So what does that mean? So let's look at that. So these are graphs showing the response to a given pulse of greenhouse gases at different equilibrium climate sensitivities, or ECSs. And so if the ECS is like, well, the IPC is like 3, so it's in between sort of the green and the blue, then you'll see that in all cases, this is 10 years, this is 100 years, this is 1,000 years. So basically, you get, for any given amount of emissions of greenhouse gas, or CO2, this is for CO2, you get about a third of the warming. You get about a third of the warming in the first 10 years, and you get the next third in the first 100 years, and you get the last third in the next 1,000 or so years. So again, what ECS is a doubling It's the warming you expect by a doubling of CO2. It's not that you have to double the CO2. It's sort of like a measure. Like if you double CO2, how much would it warm? It's just sort of give you a feel for how sensitive the climate is to greenhouse gases. And that's why it's called climate sensitivity as well. So, but this is really interesting because this is something I learned actually from reading Jim's last paper, is that the change in CO2 causes warming, right? CO2 traps more heat. It acts like a blanket over in the atmosphere, stopping Earth's heat from radiating out into space, and it makes the Earth a little warmer. But that warming triggers feedbacks. For example, melting Arctic sea ice, which is white, and it reflects a lot of sun and then exposes dark ocean underneath, and that warms the Earth. And there's other things like that warm the Earth in response to the warming. So let's call the emission of CO2 a forcing, and forcings are things that humans do to change the climate. So we emit CO2, it creates a warming, and that warming creates a warming. And that's also what you're seeing over time. And that's why these lines keep going up for 1,000 years, is that at first there's sort of an immediate warming, and then the warming causes warming. But you'll also notice that higher climate sensitivity means that any given amount of CO2 will cause more warming. And so what Jim is predicting is that 2025 will be about as warm as 2024. So what we're looking at here are the blue line and the green line are previous El Nino periods. So on the left side is the growing El Nino year, the middle is the peak El Nino year, and then the right side is fading El Nino years. And so what you see, and if we look at the blue line, the temperature starts going up. In the peak year, it's kind of high, and then it goes down in the fading year. And the green, which is 2015 to 2017, by the way, the blue is 1997 to 1999, which was a strong El Nino for back then. But 2015, the green line, it's going up, it peaks, and then it kind of goes down. It's still a little bit high, but it's kind of much lower. But now let's look at 2023, 2024, and going into 2025, the red line. And you'll see that it goes up. Yep. And you'll also see that it's kind of staying up across 2024. And in 2025, it's actually a little bit higher than starting in 2024. And Hansen is predicting that it's going to it's going to go up and down, of course, but that the average temperature in 2025 will be about the same, if maybe not even a little bit higher than 2024. Now, that should not happen if the temperature is just controlled by El Niños and La Niñas. But if the change from aerosol emissions is big, which Hansen says it is, and ECS is high, that means we haven't seen all the temperature change from the shipping emissions change we made in 2020. The warming from reducing reflective cooling, starting in 2020, that was like a big change. That has caused warming, and that warming will cause warming, as we just saw in that previous chart about ECS. So that's his bold prediction, that 2025 will be about as warm as 2024. And climate scientists who say Jim Hansen is wrong, they can't, if this does happen, they won't be able to explain it. In fact, I haven't seen anyone who's came up, they sometimes say he's wrong, but I haven't seen an alternate explanation except to say, well, it's just natural variation, which it doesn't. When you look at that other chart we saw with the warming in the North Atlantic and North Pacific, it doesn't look like it's just random. It looks like there's something happening there. So this is a bold prediction that Jim Hansen made. So one other piece of important climate news was fairly recent, and we had him on as our guest, is George Tselioudis, from a NASA climate scientist. And what he did is he looked at satellite data of clouds and found so one of the really big questions in climate science was whether warming causes more clouds or less clouds. If global warming causes more clouds, well, then those clouds will reflect sunlight away, keep the Earth cool, and it will act as sort of a negative feedback. In other words, something that would stop the Earth from warming too much, because it would, the warmer it got, the cooler, the more clouds would do work to keep the Earth cool. But if it's the opposite, if warming causes less clouds, then as the globe warms, there'll be less clouds and therefore less reflection of sunlight and therefore even more warming. It would be a reinforcing feedback. So big question mark. It's been studied for like 20 years. What's going to happen? Everyone's working at it. And George and his colleagues looked at the details of this. So let's zoom in on this. And it's kind of interesting because you can sort of see the result of the entire study in one chart. This is the Pacific and Ocean, Atlantic Ocean, or Pacific region, Atlantic region. And all you need to know is that bluish colors are less clouds. You can see total cloud cover down here below. And sort of the dark reddish and orange colors are more clouds. And you can see, just like that other chart, this is the latitude, all sort of crunched into one point. And then we have time from 1985 to 2020, essentially. This is the last one is 2015 on the chart here. And what you see is that the blue regions are expanding here and here, and the red regions are compressing here and here. And that means there are less clouds going forward as the world warms, and less clouds means more warming. And this is one reason why the ECS, the equilibrium climate sensitivity, is higher, like Jim Hansen says, at 4.5, because one of those feedbacks are clouds. That's a relatively short-term feedback. And so as the world warms, there'll be less clouds. It would make the world warmer, which supports the notion that ECS is higher than what the IPCC says. So very kind of a simple study, just using satellite images of clouds and looking where they are and where they're not, and plotting that all out. And you can read the paper. It's linked in the description below. So what does this all mean? Well, it means that there's going to be more warming than we had hoped, let's say, or that that's been previously predicted for the amount of greenhouse gases that we have already emitted. And how much is that? It's a lot. We've emitted 2.6 trillion tons of CO2. It's the number one thing that humans have made. And just to give you a little reference, the dry weight, so to remove the water, the dry weight of all life on Earth, from bacteria to whales to trees and things like that, is estimated to be about 550 gigatons, or about 0.6 trillion tons. So the amount of CO2 we have released is a lot. By the way, that's not how much is in the atmosphere, because the oceans and plants and soils absorb, roughly speaking, a little bit more than half of the CO2 we emit. So the amount up there is 1.2 trillion tons or something. That's excess to what used to be there. We've increased CO2 in the atmosphere by 50%. Roughly speaking, there used to be 2 trillion tons of CO2 in the atmosphere, and now there's about 3 trillion tons in the atmosphere. That's amazing that humans were able to do that in such a short amount of time. So what else does this tell us? Well, if the warming from greenhouse gases is more than we thought, and these carbon budgets to keep us under 2 degrees and 3 degrees were based on a 3-degree Earth climate sensitivity, and the climate sensitivity is really 4.5, well, that means there's really no carbon budget left. And it's, I think, a bad concept to begin with, because it seems like you have permission to burn that much carbon, which you shouldn't have. But anyway, there's no carbon budget left. And the other thing, this was originally a talk to a conservation policy class. And so this really tells you that when you're designing climate policies and conservation policies, you have to take this into account. You have to take into account the worst case and what could really happen. And again, we'll cover some of the policy implications in another program. So what else have we learned from Jim Hansen? So other things he's talked about in these recent papers and in a previous paper called the Ice Melt paper, which also links are in the description, is that because there's sort of more warming than we thought, and warming is accelerating now, there's going to be more melting of Greenland and the Arctic sea ice than was previously expected. Now, there's something called the AMOC, the Atlantic Meridional Overturning Circulation. We'll get into a little more detail on the next slide. But this is the ocean conveyor belt that brings warm water from the tropics to Northern Europe. And it's a very, very important current. It's why Northern Europe is a nice place to live, even though it's up around where Northern Canada is. And that's a pretty difficult place to live, or Northern Alaska. So the Atlantic AMOC is a very important current, and what shuts it down is fresh water coming in from the melting Greenland and melting Arctic sea ice, because that's fresh water. And the AMOC is both, as we're about to see, is both a wind-driven current, or wind-driven currents, but the big part of it is what's called thermal haline, or sort of a temperature saltiness current, temperature salt current. And when you put fresh water on top of that, the heat from that salty current, which is heavier than the fresh water, finds it hard to emit its heat and therefore drop to the bottom and complete the conveyor belt. So hot water on top moving towards Europe, it cools off, gives off its heat to Europe and that area, drops below, comes back. And it's a little oversimplified, but that's sort of how think of it as a conveyor belt. And what Hansen is saying, with the melting being faster than thought, and a few other differences between what he thinks and what the IPCC thinks, that there's a point of no return, what we might call a tipping point, 20 or 30 years from now, where the AMOC may begin to shut down. And once it begins to shut down past the point of no return, it's a point of no return. In other words, nothing you can do at that point will stop it from shutting down. And we'll talk about what shutting down means in a little while. And so if we shut down, if the AMOC shuts down, the warm water that was going to Northern Europe is going to hang around in the Southern Ocean. What's down in the Southern Ocean? Oh, Antarctica. And Antarctica has a lot of ice. And if we make that ice melt faster than it otherwise would, we can have a lot of sea level. I think altogether, if Antarctica melts, it's 250 feet of sea level rise, but even a tiny bit of that would cause 10 feet of sea level rise around 2100, or maybe a little bit afterwards. And that's a lot, as we'll see. And we're not going to really cover solar geoengineering today in this talk, but let's just say that probably one of the only tools we have in our toolbox to prevent an AMOC collapse is solar geoengineering. And we're going to do a whole program on that coming up very soon. So I'm not going to cover too much of solar geoengineering today. So let's talk about what the shutdown is and what it means. I mentioned that the AMOC stands for Atlantic Meridional Overturning Circulation. It's this ocean conveyor belt. The Gulf Stream is part of it, but the Gulf Stream is a wind-driven current. And again, there's both wind-driven and heat salinity-driven currents. It's been slowing down. It's estimated since the 1950s, maybe 15, 20% slower than it was. However, the IPCC has said that it's unlikely that the AMOC will shut down this century. And that's what it says in the IPCC reports. But Hansen and other people, and including many that we've interviewed, on this program, Peter Dibblitzin, Renee Van Westen, and others, say that that the IPCC is using sort of incorrect data for two things. One is the ocean mixing. If there's more ocean mixing, then that fresh water will be mixed with the salty water. It won't have as big effect if the fresh water stays on top and sort of provides this barrier. And the other thing is there's more fresh water if Arctic and Greenland is melting faster. When you throw those two things into the mix, then you can come to the conclusion that the AMOC might shut down soon. We don't know who's right, but I would say it makes sense to, as they say, assume the worst and hope for the best, because what is the worst if it shuts down? So the impact from AMOC shutdown is, well, obvious thing is a cooling of Northern Europe and Northern North America. In the places like Norway, you can get a cooling of 10 to 20 degrees Celsius in the wintertime, which is insane because, I mean, just think about it. Global warming today has only been 1.5 degrees Celsius on average. And now certain countries would drop like 20 degrees Celsius. It's crazy, crazy. Without going too much into this, storms are driven by temperature gradients, the differences in temperature in different parts of the Earth. And with global warming overall, the temperature gradients have been going down because the North Pole has been warming faster than the equator. And obviously the equator is warmer than the North Pole, but that difference is going down. And that's what's made the jet stream wavier and slower. And that's what's given us all this crazy cold weather followed by crazy hot weather. But with the AMOC shutdown, the North Atlantic will get very cold, and the temperature gradient will go way up in that region, and that will drive very strong storms, which Jim Hansen in his book is titled Storms of My Grandchildren, talking about these crazy storms that we've never experienced in human recorded history. So that's something. There'll be an extra about 2 to 3 feet of sea level rise along the North American east coast because that water that was being pushed to Europe from the AMOC will no longer be pushed as strong. So some of that will slosh back across the ocean to the other side and cause a sea level rise. Nothing to do with the global sea level rise. It's a local sea level rise. And then I think one of the biggest impacts besides sea level rise of a shutdown of the AMOC, we had Matthew England on the program long ago before we were doing YouTube programs, and we're going to have him on again, where his modeling shows that an AMOC would cause an average of about a foot a year less rainfall across the entire northern hemisphere. And that obviously impacts food productivity, plus the changes in temperature and wet, dry areas and monsoons and everything like that would just turn agriculture on its head. And as I just mentioned, there's impacts to the Amazon, monsoons, drought all over the world. And as also mentioned earlier, that that warm water not going to Europe means it's hanging around the Southern Ocean, helping to warm the Antarctica and accelerating melt of Antarctica. And this is a tipping point because in the sense that you can't change it once you decide you don't like it. It doesn't matter. It's not reversible for centuries, if not longer. But what does 10 feet of sea level rise look like? This is several meters of sea level rise on Florida. Very significant. Obviously, all over the world, there would be island nations that are submerged. Essentially, almost all coastal cities submerged or badly damaged. It's a big deal. Now, there's a paper that came out fairly recently. I mentioned it on the program earlier. I just wanted to give you a heads up. It was called Continued Atlantic Overturning Circulation, Even Under Climate Extremes. And what this paper says is that even if the Earth warms a lot, I think they even did things up to 5 degrees Celsius of warming, which is, by the way, catastrophic on many, many levels, that the AMOC will not, quote, shut down, unquote. Well, when you looked at this paper in more detail, it didn't say what you think it said. First of all, there are, as mentioned earlier, both wind-driven currents in the AMOC, things like the Gulf Stream is mostly wind-driven, and these thermal halides or temperature salinity currents. which are the major part of the AMOC. And so one thing they do in the paper is say that the wind-driven currents won't shut down, like the Gulf Stream won't shut down. Well, sure, that's true. The wind's not going to stop after the AMOC shuts down. Quote, shuts down. We'll go, what does that mean? We'll get into that in a second. So they're saying something. No one was claiming that the wind-driven currents would shut down. So that's called a straw man, where you argue one thing that no one else is arguing. And then they also said that the thermal haline currents won't go to zero. But then again, no one is saying that those thermal haline currents will go to zero. It's just that they're going to drop significantly. And that's what other scientists mean when they say AMOC collapse, is that the flow of those thermal haline currents will drop significantly. And in fact, this paper uses some of the same exact models that other AMOC researchers use. And again, not the exactly same picture showing reduced AMOC flow. The other researchers labeled that AMOC collapse or AMOC shutdown. And this researcher, or these researchers, named that same exact picture no shutdown, because it didn't go to zero. But no one, again, claimed that it would go to zero. So you have to watch out. And this obviously got some coverage because some of the conservative media outlets want to make it look like everything's going to be okay. So you got to be careful when you look at these papers and see what they're really saying. But watch out for that one. So what does this all mean? Well, it means that climate change is here now, and it's stronger than we even thought, especially at this point. It's above 1.5 right now. And it's also our future for sure. And, we're going to be living in a climate change future. But learning about this stuff is exciting. It's empowering to know more about what's happening. And I have to admit, it's also a bit scary, so you have to watch out for that. Something that Jim Hansen wrote about long ago is something called scientific reticence, and it deserves its own program. But in a nutshell, the academic process is set up to avoid making claims about the worst case. In other words, if you want to publish a paper, you have to be sort of 95% sure that you're right, because it's much worse for your reputation to publish a paper that turns out to be wrong than to not publish a paper about something that would turn out to be right. So for example, if you're 95% sure that sea level rise is going to be, let's say, 3 feet or more, you'll publish a paper and say, we predict, 3 feet of sea level rise. But let's say you're, pick a number, 50% sure it's going to be 10 feet. That's only 50% sure. So you can't publish that paper because it hurts your reputation if you were wrong. But the fact that there's a 50% chance that sea level could be 10 feet is extremely important information that we should all know about and plan for. Because even if there's only a 10% chance of that, that's extremely damaging and requires us to act urgently. But that's not the way academic science is set up, which is fine for things like black holes, astronomy, or whatever. But it's not okay when it's about climate and the world we're going to be living in. And so we have to not just focus on the best case, which in general tends to be what the IPCC is showing us. And by the way, the IPCC isn't showing us a friendly, happy world, but still, it's sort of more optimistic than I think it should be. And so what happens to get hope about the future is to act. Just hoping is not a strategy, but action is a strategy. So let's use climate science and to figure out what we should be doing. And again, in another program, I'll be talking about some policies that can address climate change and what to watch, what pitfalls to watch out for when you're coming up with climate policies. But that's sort of the end of the climate science side. And so with that, I'm going to invite Stacy to join us, and I have not been following the chat since. Let's go to here. Hey there, Stacy.
Hi, how are you?
Let me turn my volume up a little bit. There we go.
Um,
Let's go to this one here. I think the two of us. Whoop, whoop.
yeah, it's been a very lively chat. Thanks for changing the settings so that we could get real-time conversations going, and many are going. Um, One of the ones recently that, of course, you and I both would jump on is about EVs. This is a little bit of a tangent, but it's like, do they help or not? And I agree with the statement that they do help. They are so much more efficient, but I also agree with we should just have bikes and transit, really. Most highways should be replaced by trains. But anyway, that was one on
Well,
there that I
I
wanted
mean,
to
but that's
go on.
yeah. So EVs, it's you're right. So if you're designing the world to protect the world as much as possible, then you design a world filled with mass transit, bicycles, walkable cities, these kinds of things.
Yeah.
That's not the world we live in, and so then you have to say which is better. So neither is maybe good, right? The fossil fuel cars versus EVs, both have negative impacts on the environment. EVs have less negative impacts on the environment.
Okay,
One
I'm
way to
going to.
think about it is that if you're driving your EV, and we have to assume a kind of a cleaner energy future where the electricity you're powering your car uh, isn't full of fossil fuels. But even if it is, EVs are so much more efficient. They're about 90% efficient, where a fossil fuel car is like 20% efficient in terms of turning energy into motion. So, so they're still better, even driven by fossil fuels. But let's assume a cleaner grid. Um, your fossil fuel car, you can imagine you're driving next to a 4,000 gallon tanker truck filled with gasoline, because that's your car. Over time, your car's going to burn around 4,000
Yeah.
gallons of fossil fuels over its lifetime. So just imagine those two cars driving down the road together, and that's what you're driving in a fossil fuel car. Whereas on an EV, if you wanted to translate all that electricity to oil, you would have a much smaller tanker truck next to you, I guess, is one way to think about it. But walking, bikes, everything, walkable cities and things like that are much better solutions. I agree.
Yes, and I will channel my inner Kevin Anderson and remind you that the world is going to change. And
That's
it's
right.
just a matter of how we want it to change. So we have no choice in the fact that it will change. So I would prefer to change that in a way that we move differently, radically, so that it is we can combat climate change and a whole host of other social and health issues.
Yeah,
Yeah.
and in the next part of this lecture, this was like a 2 hour lecture that I gave, and the second half is about what to do, and I wasn't really talking about that today, but I would agree with you that one of the things that is not available to us in the future is the status quo, because people want to compare, let's say, the clean energy future or something, or changes in our lifestyle to what we're doing now, and that's what we're doing now. But in the future, what we're doing now will not be one of the choices. It's either make these changes or suffer even more. And people don't get that. I mean, it's just outside of their point of view. So we'll talk more about that, I guess, in the policy lecture part when we do that program.
I have for myself, I have a completely just random question that came into my mind as I heard you talking. And then I do have a few YouTube questions. How would you
Okay.
like me to go about it?
Well, what's
Just
your question first, and
My
then
question is, I remember you were saying, and you've said this before, about the follow-on effects, like the warming is going to cause warming.
Mhm.
And it just made me wonder, is there any cooling that could in, make more cooling happen?
Yeah. Actually, we're gonna. I just invited a guest. Yes, last night actually
Oh,
about this.
wow.
But we didn't respond to it because it was just last night. But there's a new paper out very recently, the last week, I think, that says if we do solar geoengineering to stop overshoot. So, okay, so the overshoot is like we pick a climate target like 2C, right? Well, there's no way we can stop at 2C, but in the fantasy world where we're going to drop our emissions to net zero in 2050, 60, pick your number. Once we get to zero emissions, then CO2 will drop because the oceans will keep absorbing CO2, and temperatures theoretically are going to drop over time. But so what you do is you first go over 2 degrees and then you get back to 2 degrees sometime later. So they said, well, what if we use solar geoengineering to stop at 2 and go at 2 until finally it would have dropped? And they found that doing that obviously stops you from going over 2, number one. But number 2 is you drop faster when you sort of meet up at the far side, because the cooler Earth stopped the ocean from warming more, so it's easier to get the Earth to cool. So it's
okay.
so another way of putting it is that solar geoengineering, again, very controversial subject. Many people are against screwing around with the climate, but I always say, well, should have thought of that 200 years ago. But but it will not only cool the Earth directly, but will cause cooling on its own. So I think that's an answer to that. Another thing, and by the way, that was true of, we're seeing the opposite of that by getting rid of the accidental solar geoengineering we were doing with ship pollution, right? So that's the opposite. So what are some of what do you have in the chat here?
Okay, so in the chat, well, one that just came up recently and has been this one guy in here is talking about how Northern California is, we've been saying widespread drought will happen across the globe. And he's pointing to Northern California and saying, oh, we're supposed to get wetter. And it's like, I don't even know if that's true. He also said something about San Francisco having a cold upwelling, etc. And I will say, I was saying to my son last night, I don't know if you could get me. I would love to live in New York or Europe for many other reasons, but I don't know that you'll get me to move from San Francisco because for whatever reason, we are so blessed with this climate. It's just unreal. We do not, when the rest of the nation is boiling and flooding and whatever, we just don't have the same thing happening here. And so
we're on the
uniquely,
ocean, and
right.
the ocean moderates, and we have westerly winds. So we, for the most part, and
but LA is also on the ocean, and it's been, at times quite miserable there.
And they also do have, of course, that's when they have Santa Anas, where the winds are going the other way, and they're getting the hot air from the inland.
True.
But so in general, this is high level, and actually, everyone can check out the interview we did with Daniel Swain, who's like an expert on California climate and weather, and talks about this. But in general, in the United States, the West is getting drier and the East is getting wetter. The average precipitation across the United States isn't changing very much. And sometimes climate deniers like to make that point. Oh, the U.S. climate precipitation is not changing. But that's not really helpful to the people in the East or in the West, because as they get worse in either direction. So in the West, in general, we're going into a mega drought where it's getting drier overall. It's punctuated by very wet conditions, right? So the extremes are getting more extreme. So when we have rain, there's even more, and we get flooding and things like that. But a lot of the times we get drought, and some years are wet years, but we're also punctuated by more dry years. And but that's like a whole separate program with someone like Daniel Swain. So check that one out.
Mm-hmm.
I'm a super high level answer to that.
Another is what would be the impact on the Amazons if the rainforests were to disappear due to deforestation and forest fires?
Well, actually, so there's a number of things happening there, right? The Amazon, first of all, creates its own weather, right? It's a rainforest that creates its own rain. And we have been deforesting it mostly for growing food for cattle. right? That's the big thing, growing soybeans and stuff to feed cattle and humans. But also what's been changing is the weather itself, the climate, as it gets warmer. And so we've been having droughts in the Amazon. You're not supposed to have droughts in a rainforest. And so that has been getting worse. And people are very worried about it. And if the AMOC collapses, that's actually going to it's going to really hurt the Amazon. And the Amazon, what it could happen is it could collapse from a rainforest to a savanna. And then that, all that carbon that's in there, the biodiversity that is there, would be wiped away. So we're hurting the Amazon in two ways. One is by emitting greenhouse gases that warm the earth and put a stress on the Amazon. Plus, we're cutting away at the edges of the Amazon and cutting it down. And remember, it creates its own weather, its own rain. So after a while, it's a feedback mechanism where you have a little less rain now because you cut back some of it, and that itself reduces the Amazon. And if you hit a tipping point, it's gone. And soon, I mean, this century, it could be wiped out. So it's a very, very serious issue.
Agreed. One of the other questions was, well, Stephanie asked, what does the gray shadow mean? And I did not pick up on that.
Oh, on the chart?
Yeah.
The gray shadow was the peak temperatures of any year. So that was just showing the highest temperature for that month ever. And best to ignore that in that particular chart. But that was what the gray shadow was. I should have mentioned that. But that just the peak temperature from any time. And that way you can tell when you're in any time before 2023. So that you can see what the current temperatures, which ones are records. So you can judge that by showing what the previous records were. And we have, by the way, I'm going to let Leon in here, and Eli are here as well. So they're welcome to.
Yeah, there's a question that Leon was going to answer, and I didn't quite understand it. So I'm glad he said he would answer it.
What's that?
It says question 567, Leon Simons this morning. Can you talk about it, Dan? Thanks. So
567, what?
I don't know if I copied
Leon, are you on there? Can you join? I don't know. I see your microphone and everything. I don't see your picture, but he might not be there. Well, if you can pop that one up, maybe I can see it. I don't know what that question means. So let's find something else.
It was at 10:39.
Oh, there he is.
It was at 10:39 from Robert.
I think your mic might be off, but check that.
Yeah.
You're muted.
Getting ready.
You're muted.
Am I muted?
Oh, no, I hear him.
Not hearing you.
I hear him fine.
Okay. Well, Stacey, do you hear me now?
Can't hear you, Leon.
I can hear you.
Check your mic.
Yeah.
It's strange.
It is showing up as X'd out. Your mic is X'd out.
I don't know why I would hear him and you wouldn't, but I do.
Go to settings. 10:39.
Can you hear him on YouTube? Because Eli hears him.
Oh, you do hear Leon? Do you hear Stacey? Do you hear him?
I hear him. I've been hearing him, and
something
Eli
happened
hears
to my
him.
thing. Hold on.
Sam on YouTube hears him, so I don't know.
Let me sign out and sign up again.
Okay.
In the interim, there is one comment I absolutely loved. Biff said, Trump has solved climate change. No one talks about it anymore.
Okay. Now I hear.
And now I hear an echo of me.
I hear echoes of everyone.
Okay, let me try to switch to. Wow.
So
I hope you don't hear music. Let me.
No music.
Wow, that's a little weird. What's going on? Let me try to change my audio to AirPods.
So there was a YouTube comment that everything was
go.
clear. So maybe the echo is on Restream.
Maybe,
yeah, but try Leon. How is the echo now?
No echo. Yay.
Right.
It's
so
gone from AirPod.
Maybe my audio switch got messed up for a second.
And I did want to mention Nadia made a comment of Beckwith just covered a paper on high precision in situ aerosol forcing measurements of negative 1.16 watt per meter squared. Just noting that.
Yeah, okay. I haven't seen that yet from Paul. But that would be if from memory, if I remember, they were saying the ship emissions were 0.5 or something versus 0.05 from the IPCC, assuming over the ocean. So, but you have to make sure you're doing apples and apples there. So I can't really comment because I don't know what that one's about. I see Nadia talking about from Albert Bates, one of our friends on Climate Chat. The entire UN FCCC or IPCC process were already successful interventions by the fossil fuel lobby to paralyze all climate action. Well, especially with the COPs being run literally by fossil fuel executives. I mean, you don't have to know much more than that. But
and then and then Nadia mentioning that John Sununu is on tape saying that was what they were intended to do.
Well, I don't know if John Sununu saying anything. But are you hearing a popping, by the way? Because I'm getting a popping in my.
No, but early on, I was hearing something that you, like something, when it was just you, I was hearing something that sounded like popping or keyboard typing, and I don't know, but it's gone, so.
Oh, I see that thing about 5, 6, 7. I don't know what that means.
Oh, another question. The big blue blob, will it grow larger? And I say, yes, it will. And that's the beginning of the AMOC shutdown. But
hey, Leon, welcome. Let's see if it will all work here. I think my audio might be working now. All right. So what is question 5, 6, 7? What does that mean?
Yeah, that's about...
what answer that one?
A graph I shared today.
Yeah. Oh, no, wrong one.
Do you hear me?
This one.
I hear you.
Yes, we can. Go ahead.
Okay, perfect. So sorry. Yeah, so that was a graph I shared today. Oh, and this one, I think you'll see it soon.
Okay.
Can you see it? And share it?
Not yet. Let me. How do we do that? Do I have to? I don't see anything popping up or anything permission-wise. Do you see it on your screen, Leon? Oh, here we go. Oh, nope.
Yeah,
that's me. Go ahead.
I'm sharing my screen, but it's.
I don't see anything about screen sharing. Let me try to get to. Let me see. Go to this. I don't know. Well, maybe I just describe it and. Or just tell us what it's about. Are you frozen, Leon? You look frozen.
Yeah,
All right. So why don't we?
So one other. Well, did you have any comments on the blue blob? Do you agree with?
Wow, that's very strange. Let me get Stacy back here.
Oh.
It's very strange with Leon being frozen. I don't even see him listed as a guest anymore, but his thing is that's because he's trying to share. That's why. But Leon, I don't even see you in the guest list now. Oh, there you are. Source is not shown. Okay. There's your screen. We're not seeing anything, Leon, and you're still frozen. So let's. I'm going to turn you off, Leon, because I don't know what's going on there. I'll turn you on in a little while. Let me get this over here. So what? Well, sorry, what was the question again? The blue, the green,
Blue
the
blob.
blob, the cold blob. By the way, it's called the cold
Cold blob. Yeah.
So because the AMOC is slowing down, there's less warm water reaching down as it turns around and comes back near the southern tip of Greenland. And so when you take a look at all of global warming across the entire globe is warming up except for one place below the southern tip of Greenland, and that's getting colder. So when you look at a global map with the red as being, hot and blue being cold, there's a blue blob or a cold blob below the tip of Greenland forming because of, on average, not all the time, but on average, because of the slowing of the AMOC, or at least that's what people think it is caused by. And so as the AMOC cools even more, that cold blob can increase, except remember the entire world is warming too. So I don't know how that's going to impact the overall blue blob. But yeah, if that gets bigger, that's a sign that the AMOC is getting weaker. So that's a bad thing. I'm going to try turning Leon on again, and I don't see his screen. Yeah, Eli, go ahead.
I wanted to comment on that. This in Hansen's newsletter at the beginning of the month, he was talking about warmer currents lower at depth in the ocean, right? And that's kind of the correlate of the AMOC slowdown. But it doesn't just, everything doesn't stay where it is. The water that was circulating downwards instead goes into the Arctic basin. And a lot of I want to step back and reference the way climate scientists, will always focus on the IPCC models as their true north, right? Mm-hmm. And those models have a lot of, it's assumptions layered on assumptions, because the calculations are really complicated and you need assumptions, right? And among those assumptions are that, well, this other effect will only be within this certain range, right? And when you look at what the overall CMIP models say about how likely it is to warm at the depth that cloth rates occur, for example, it'll be a number that's based on, running the calculation several times, and the average will reflect the assumptions that are buried several layers deep, right? When instead we see measurements, right, that things are warmer at these depths, and I don't know the detailed information about how much warming there has been at the gas hydrate stability zone where these cloth rates are, but it had been the conclusion that has been said very confidently by the broad consensus of climate science is that we don't have to worry about cloth rates before, right? Mm-hmm. Now, however, we are seeing warming at those depths, which was, again, something that depended on several layers of assumptions. So I think that really needs to be revisited.
Well, and also, by the way, you bring up a point that I should have made more clear. What I'm presenting today is mostly the science of Jim Hansen and Leon Simons, who was on just earlier, hopefully get him back, and others like George Tselioudis. And it's not it's not the mainstream consensus of climate scientists, but it's not like, so that some mainstream scientists say, well, they're not right, but they also don't explain the measurements we see. So Hansen and others are the only ones who are giving an explanation that fits the data we're actually measuring. And so that's number one. That's one reason I would go with Jim Hansen. Number two, he's been right all along, in the long run about the important things. And he looks at the climate as a system. He's not like a cloud particle physicist only looking at droplet size or something like that, or only looking at deep ocean currents. He's looking at the whole system. He looks at paleoclimate, ancient climate history. He looks at satellite measurements. He looks at models. He takes the whole thing into account. And so that's another reason. But the other reason is that we're talking about existential threats to humanity. And when you do that, you need to, assume the worst and hope for the best. So you want to know what the worst case is, because that's what you want to protect against. So I'm not saying 100% sure that Jim Hansen's right about this, but if I had a bet, I would bet that he's right. And the data fits his theories. And we're going to find out this year, if 2025 remains a hot year, it's really hard to explain that without assuming the ECS or the climate sensitivity is 4.5 degrees, like he says, versus 3 degrees, like the IPCC says. So, it's not like we'll find out 50 years from now. We're going to find, we kind of know now by looking at that ocean temperature graph, but we're going to get more and more reinforcing evidence, and eventually, just like the scientists who disagreed that the climate warming is accelerating, they kind of changed their tune over the last couple of years and kind of agreed that, well, yeah, it seems to be accelerating. But again, they'll come around, I think, to the other things Jim is saying as well. Let's see if we can, Leon, I don't know if you're there, but you can join by audio, but you are turned on.
Yeah, do you hear me?
You want to know that. Yes, I do hear you. Hear you loud and clear. That's great.
Okay, great. Let me just.
You wanted to maybe
I won't switch on video because I think my connection.
Yeah, and that the screen sharing, which I can see, does not show anything. It's blank.
So that was, I'm trying to do it because I have his graph.
Oh, well. Oh, okay.
No,
let's see. I'll turn that on. Here we go.
Let me.
There we go. Oh no, we got it on.
I got it, Leon.
It's there.
Do you see it?
Great. Well, yeah. So this raised was about this graph, and now Stacy started sharing the screen.
Yeah, we can see
graph.
it.
So my value was a bit higher because I recalculated it, but it shows the 100,000 years. Shows the CO2 equivalent, which means that the CO2 concentration. It compares the CO2 concentration and methane, dioxide, nitrous oxide, concentrations. So all the greenhouse gases, how they changed relative to 1950 when the Industrial Revolution. And then it pretends like the other greenhouse gases.
By the way, you're breaking up.
And the changes.
Your voice is still breaking up, but okay, go ahead. I'm not hearing you at all. I think what Leon's saying is this is a graph showing total greenhouse gas, so CO2, and then converting other greenhouse gases like methane and nitrous oxide to a CO2 equivalents. And he's saying that as of now,
yes,
2024, the total greenhouse gas equivalents, everything switched into a CO2 equivalent format, is 567, which is double pre-industrial CO2. CO2 pre-industrially was 280 parts per million, and doubling that would make it 560, and this is showing 567. So he's saying that if you look at equilibrium climate sensitivity, that's the theoretical doubling of CO2. Well, today we're at a doubling of CO2 equivalent. And if we maintain that for 1,000 years, that we would go up to 4.5 degrees. But of course, we're still increasing greenhouse gases. So we could hit 4 degrees by the end of the century if we actually just keep pumping CO2 and other greenhouse gases out into the atmosphere. So not a good thing. Did I get that right, Leon? I don't see Leon now. Actually, I think we lost him. Okay, Stacy, any other questions?
Is the graph off now?
Yeah, now it is.
because I'm not skilled enough at this. So
Okay.
I wasn't, I don't have that open. So yes, there was. When do you think we will get to a blue ocean event?
Well, everyone's. So, what is a blue ocean event? A blue ocean event is when the Arctic sea ice in the minimum part of the summer, when there's less Arctic sea ice in the summer, and the winter grows again, and it shrinks again in the summer. September, I think, is the minimum. When is it virtually gone? And virtually gone means less than 1 million square kilometers. So still, a reasonable amount, but you have to. It's never going to be all gone. So the blue ocean event definition, when is it mostly blue ocean instead of ice, is 1 million kilometers or less. The minimum was in 2012, and we're talking about the extent, not the volume, so the area of sea ice. And some people keep predicting it's going to happen anytime now, and it always seems to take longer than we thought. So I thought we'd have a blue ocean event by now. If you look at my climate talks from 2008, I thought it would be within 10 years, but was wrong about that. So I think it's maybe in the next 10 years, or 10 to 15, because for whatever reason it's I don't know. It's tricky. Now we are at the minimum. We did have the maximum sea ice this year. In other words, when it grew to be the biggest for the year, it was less than ever before. And now I'm going to hold on. That was Leon's feedback. Okay, I turned that off. However, even though you think, and it's really dropping quickly in the summer, it always kind of levels off, because 2012 had some special conditions that really made it drop a lot. There was sort of the storm in the center mixing up all the ice and stirring it up, and really reduced it drastically. We have another one of those storms along with the extra heating that we have today. It could happen faster. But the answer is, I don't know.
Was there anything that led up to those storms that it might be a marker for it happening again?
Well, I think it was warming and the changes. It just happened to be. It was more like a whole bunch of things happened at once. Like it was that could happen again. But
Okay.
But that's why even the last years, when you really think it's going to be the minimum, the curve bends around, and 2012 is still at the bottom in September. Now it's going to change. The other years are getting closer and closer and closer to 2012 as we go on, and eventually it's going to drop below. So if I had to guess, 10 years, but I don't know.
Well, this
Okay.
is why calling it climate disruption is more apt, because disrupted systems are harder to predict, right?
Okay.
Another one is from Jean. I used to hear about a methane bomb. What is happening with the methane levels and risks?
So that's a little bit something that Eli was talking about. There's something called clathrates. And what a clathrate is methane molecules sort of in an ice matrix. So think of it as ice crystals with methane in them, or like a snowball made of ice and methane. And that they can only exist in the deep ocean, where under cold temperatures and high pressure. Now it's even colder in the Arctic, so they exist higher up in the Arctic oceans than they do in the Atlantic Ocean, let's say. And there's a lot of methane in those clathrates. A lot. I think more than all fossil fuels we've ever burned, by a big factor. So if things warm so much that those methane clathrates in the deep ocean melt and give off their methane, we're in a lot of trouble. Now, in the Arctic Ocean, where it's warming even faster than the rest of the globe, and where clathrates exist closer to the surface, these clathrates are melting already, but most of the methane is absorbed by the ocean before it hits the surface and gets into the atmosphere. But that could change. And so that's what the methane bomb is as we get so much warming that these clathrates come out, get into the atmosphere, and cause a huge amount of warming, because methane, while it's in the atmosphere, is 120 times more powerful than CO2 on a weight-to-weight basis, a ton of methane versus a ton of CO2, than CO2 is. Now, the good thing about methane is it disappears, it sort of breaks down into CO2 in around 15 years through natural processes. And so it's, whereas CO2 lasts for hundreds of thousands of years in the atmosphere once it's up there. So it's we've talked a lot about it in the past, but that's in a nutshell what. Now, if the warming gets so much that the deep oceans melt the clathrates, then we're already in a world of hurt already, that the world is that warm, and there's a lot of other big problems happening. So that's also, I think, why scientists say that's not the problem to worry about right now. An AMOC shutdown is probably much sooner than a clathrate bomb, but things are possible.
It's complicated, and it's more the uncertainties that are why I talk about it a lot, because people just kind of like don't want to deal with it, but we may not have the choice of not dealing with it. And if we think ahead, maybe we can prepare. I think there are ways we can prepare, but in addition to the phenomena that you described, so it's a particular, the gas hydrate stability zone. It's a range of pressures and temperatures, and on either side of that, the methane becomes gas. And so you have the situation now where melting in Greenland, I believe in Greenland, but I've seen it definitely referred to in Antarctica, where the uplift due to melting ice, there's less ice, it's pressing down less on the continental shelf of so the sediment of the ocean shelf comes up, and that is causing some clathrate destabilization.
Okay,
that kind of counteracts the pressure changes due to sea level rise, right? So it's very complicated, and we don't know how it'll all shake out, but it's the monster on the bed that we probably shouldn't ignore.
Well, that's what we tend to do, is we just create problems, and if they're not immediate problems, we ignore them until they become huge problems. That's the way humans operate. Let's
Nadia,
just get another question or two.
Well, Nadia had commented earlier, the clathrate gun is going off right now, and the East Siberian Arctic Shelf, Laptev and Kara seas are massively bubbling. Never mind all of the talics exploding all over Siberia. So,
well, there's been reports of that for at least the last 10 years, and it is bubbling up. You can find places where there's bubbles. By the way, it's just just for reference, CO2 levels in the atmosphere are 420 parts per million, 0.04%. Methane levels are 2 parts per million, but actually closer to 1.9 parts per million. But it used to be 0.7 pre-industrial. So that sort of 1.2 ppm increase is huge, because you got to multiply it times 120 to because it's so powerful a greenhouse gas. But it's something we have to keep an eye on. It doesn't seem to be out of control yet, even though it is going up. And it might not just be clathrate, but permafrost. So permafrost is frozen land that used to be permanently frozen, and when it melts, if it's dry, it gives off CO2, but if it's wet, it gives off methane. And so that's also a potential dangerous feedback of methane in the climate system, because the amount of CO2 in the permafrost is twice as much as the entire atmosphere. So you only need to melt 10% of it to have a big problem. And if it comes out as methane, it's even a bigger problem. So let's do one more question. And
I have one final one for funsies here. Which science fiction film scenario do you think we will face based on what you described today?
So I think the most, and I'm not the only one who thinks this, but I think the most accurate film about climate change is a movie called Children of Men. And it's from a while ago, and it's not about climate change. You don't know what it's about. Something bad is happening. and you're not sure what it was, but the rest of the world has just collapsed. Society has collapsed, except in England, where it's under martial law and I don't know, stiff upper lip or whatever it is. It's keeping them still with some level of civil.
Carrying
keep
on.
calm and carry on. And there's also another aspect of it where no one could have children anymore for whatever reason. Again, nothing's explained, but the world that it shows how people are getting by in this very, very stressful world where the rest of the world is collapsing, I think is a very interesting and view. And so check out Children of Men. Also some amazing, so there's a 10-minute scene where they're running through and there's gunfires and there's explosions, all with one, well, it appears to be one take, which you think, how is that even possible? So check it out, Children of Men.
Along those lines, I'll drop in my family-friendly WALL-E.
WALL-E, yeah, that's true.
You don't know what happened, and it's just the humans that are left are just larger,
fat and floating around.
Yeah. And the robots are picking through the rubble that is or was our Earth. Yeah.
And I also say, of course, Don't Look Up. Adam McKay, we had him as a guest.
Oh my God!
Check out that program. Now that's not about, well, theoretically it is about climate change, but it's about a comet coming to hit the Earth. But it's more about how we react to that and not react to that. And that is absolutely dead on. In fact,
100%.
In fact, they have a news interview where they're interviewing the astronomers about the comet coming to hit the Earth. And they're asking her about her dress and stuff, like, rather than the world's going to end. And then some, I think it was Just Stop Oil people were arrested and on a real news show. And someone put them together and you could not tell which was real and which one. They were asking her about her dress on the real news show. It was absolutely wild. And so
what are you wearing? Yeah. Who are you wearing?
So if you haven't seen, I think most people watching this probably have seen Don't Look Up, but that was certainly
several
top
times,
tier
like us.
in terms of the political response to climate change. That definitely had that. So that's a good way to end, I think. So there is another part of this lecture which I will do sometime. And let me say, so next week, if it all works out, we're going to be doing a really interesting show on solar radiation management. Maybe I'll do the policy show on the 27th. And we do have some other really interesting guests coming up as well. So, actually in May, Renee Van Westen coming back again.
Oh, great.
Talking about AMOC and stuff. So a lot of interesting things. If you have guest suggestions, let us know. You can put them in the comments. And please, I forgot to say it.
Like and subscribe.
Let me find my captions here. Yes, I'll put it across. Like and subscribe. We don't do a good job on this show of encouraging you to subscribe, hit the like button, all that kind of thing. But
tell your friends.
Comment. But it is actually important because this is not just a show about cats or Macs or whatever the hell Tesla is. This is a show about climate change that in fact affects your life and your children's life, all your friends and family. And the more people that know about it, more people that are concerned about climate change and understand the situation we're in, the faster we're going to do something about it. So it's not just for YouTube, but it's really to spread the word. So please like and subscribe, tell your friends and all of that, and put a comment about what subjects you'd like us to cover in the future. And with that, Stacy, thank you. Eli, Leon, thank you. And we will see you next time. And thanks for joining us.
No.
Take care.
Bye-bye.
Bye-bye.